So now understand entropy as a concept, as a measure of disorder. We just talked about how motion is intrinsically tied to that idea. And then that brings us to the third law of thermodynamics, okay? The third law of thermodynamics says at 0 Kelvin, the entropy for systems, right, equals 0. Now notice it's not a delta S, it's an S. So at 0 Kelvin, if we think about what that means from a physical standpoint, remember you're given a temperature here, and temperature measures kinetic energy. Temperature measures motion, okay? So at 0 Kelvin, essentially, everything is freezing up, and you're getting to this situation where it's solidifying, it's crystallizing, and in fact, even the molecules inside that crystal are not moving. Because if they were moving, they wouldn't have a 0 Kelvin temperature. So again, tying disorder to motion, there's no motion at 0 Kelvin, so there's no entropy at 0 Kelvin. That means when you're looking at a change in entropy, if you're looking at entropy at some temperature away from 0, okay, a delta is always final minus initial, right? If I set my initial to 0 Kelvin, S at 0 Kelvin, that's what this symbol means. S at 0 Kelvin is 0. So delta S's, especially delta S's of formation, if they're referencing 0 Kelvin, okay, then you don't have a delta S, you have an S at that temperature. So for example, the table temperatures for delta S formations are often tabulated at 25 degrees Celsius, okay? So what that means is inside that table, remember how we looked at an equation that was exactly like this, but for delta H? And inside here, there were delta H's of formation. That table is referencing 0 Kelvin. It's using the third law of thermodynamics. These S's are measured at 25 degrees Celsius on your table, okay? And so delta S for the reaction doesn't depend on delta S's of formation. It depends on S's of formation, okay? Now, like the reason I bring this up is you should be aware that the third law of thermodynamics exists, but you'll see that this tabulated information is markedly different. There's 3 columns in a table. One has delta H's, one has delta G's, which we'll talk about in subsequent videos, and one has S's. Not delta S's, but S's. And that's because the third law of thermodynamics was invoked, okay? So the reason we bring this up is because you need to know how to use this, just like you would for delta H, but what you'll see inside are S's instead of delta S's. That's because somebody used the third law of thermodynamics to fill out the information on that table. These are still stoichiometric coefficients. You still do the sum for the products, and then you do the sum for the reactants, okay? The exact same process, except you're looking for S naughts instead of delta S naughts of formation, okay? So this will give you the entropy change for a reaction, and it'll give you a number, and it'll also give you a sign, okay? So remember, we're still not talking about delta S for the universe here, but imagine you carry out this process, and what you get, right, let's title this. Let's look at the sign of delta S, not delta S of the universe, but delta S for a reaction, okay? So let's say we do a calculation for this and we get like a delta S naught, okay? And then this is like gonna be the entropy change for any process, or the ideas that we talk about here are gonna be universal for any process or any chemical reaction. Let's say you enact this math, and what you get out is a delta S for your reaction that's positive. What does that mean physically? This has nothing to do with spontaneity. It's not delta S of the universe. If you do this math, you'll get a delta S that's positive. All that means for us, the way that we interpret it, is that disorder increased. When you look at delta S without a subscript, when we're talking about delta S for the system, the only information it gives us is disorder information. Sometimes you'll do this math, and you'll get a delta S that's negative. When a delta S is negative, that means order increased because disorder decreased. So again, nothing about spontaneity, nothing about whether it'll happen or not. But if it does happen, right, the reaction is going to increase disorder if your delta S is positive, and the reaction is going to decrease disorder of your system if delta S is negative. And then books and Chem 101 and professors like to answer or ask these sort of questions for you to be able to answer. And the types of examples that we're going to go over next are predict the sign of delta S. So what if we didn't have that table? What if we had to go ahead and predict the sign ourselves? Remembering that if we're looking at delta S, it's not delta SU, so we're not talking about whether it happens or not. We're just talking about disorder, okay? So I'll give you a chemical reaction. 2H2 gas plus O2 gas gives 2H2O liquid. Now, if this happens as written, right? If this happens as written, we have 3 gas particles on this side. How much motion do we have relative to 2 liquid particles on this side? All right. If you just think about it as from a disorder or an order standpoint, let's make order arguments first. Okay. Don't even look at states. I have 3 things over here and I have 2 things over here. Okay. So which side is more ordered? Well, I'm combining things. I start with 3, I end up with 2. This side is more ordered from the number of particles standpoint. Okay? 3 things became 2. Order was enacted to make that occur. Okay? Now let's look at the state standpoint. Over here I have 3 things that are gases. So 3 things that are moving around rapidly. Over here I have 2 things that are liquid. So they're moving, but they're definitely feeling each other and they're not moving around as much. Okay? So from a state standpoint, okay, motion going from the reactants to products has decreased. Okay? Order from just the counting of the number of particles has also decreased. Okay? So, order has increased. Right, let me say that again one more time. Sorry about that. Okay, from a state standpoint, motion has gone down, so order has gone up. From a number of particles standpoint, 3 became 2. So there's like a condensation of particles. They condensed. All right, 3 became 2, so order has gone up. So for 2 different reasons, what we'll say here in terms of predicting the sign of delta S, all right, order has gone up, right? So disorder has gone down. So if disorder has gone down, delta S is negative, right? Delta S is negative. Right. Let's do another example. Let's look at C2, H6 gas, in equilibrium with, must be doing this at a high temperature, 2 carbon gas, all right, plus 3 H2 gas. So when we predict the sign of delta S, we look for motion and we look for number of particles, right? Over here we have 1 particle in the gas phase. Over here we have 1, 2, O plus 3, 5 particles in the gas phase, right? 1 particle became 5. 1 became 5. It broke into 5 different parts. This is a gas over here, so it's moving, and these are gases over here, so they're also moving. So we really can't talk about delta S in terms of states because everything has the same motion, but 1 thing became 5. Order decreased. It was 1 ordered object on this side. And now it became 5 disordered objects on this side. Order decreased. So disorder, delta S, it increased. There's one thing moving over here. There are 5 different things moving over here. Your disorder increased. It became more disordered. Okay? So just with these like motion arguments, we can predict signs. So let's just do a couple more examples. Because there is a bank of problems that you'll have to do where you'll have to be really comfortable with this. So what about a state change? What about carbon, which is in a diamond form, going into carbon that's a graphite form? Diamonds are these crystals. They're ordered. They have symmetry. There's a ton of order in a diamond, right? Graphite is far less ordered than a diamond, right? Graphite, if you have a graphite pencil, you can just drag it across the surface and it comes off, right? There must be more motion here because the holds are less strong. It's easier to manipulate this thing physically, graphite, compared to diamond. Diamond is very ordered. Graphite is less ordered. As we go in this direction, as it's written, right? This has a high order, and this has a lower order. All right, lower order. So our order from left to right, the way it's written, has gone down. So our disorder has gone up. Oops, sorry about that. So again, we can predict the sign of delta S even for phase changes, right? Even for phase changes, okay? Always when you're doing these problems, think about, right? If I'm not given information, if I'm not given numbers, if I'm not given qualitative, if I'm not given quantitative values, if I'm not given numbers, look for motion, look for order, look for states, look for a number of particles, and make order arguments, and then translate them to disorder arguments, right? But what happens if you are given numbers? And let's try to actually work towards delta S for the universe. Let's talk about math involving delta S. There are a few different definitions that you kind of need to just know. We're going to state them as facts, and then we'll make sense of them, but then we'll show their use, right? So we made these arguments before, right? That delta S, the change in entropy for a process, must depend on the temperature, the motion, and also the heat. Because how do you make changes in temperature? You apply heat. So there's an intrinsic relationship between motion and disorder, heat and kinetic energy. It's all sort of interrelated. And the way that it's interrelated from a mathematical standpoint, and we're stating this just as a fact, is delta S is Q over T. But it makes sense that Q and temperature play a role in disorder because this is how I make things move faster, and this is a measure of how fast they move. So delta S is Q over T. Now, because we're doing things under isobaric situations most of the time, our Q is often replaced with a delta H, okay? So a delta H stands in for Q because enthalpy is the heat under isobaric conditions. And so this becomes a way of taking delta H information and getting delta S information. So a real quick example, let's say we were doing an analysis for a process H2O solid to H2O liquid, and we were doing this under standard conditions of 1 bar or about 1 atmosphere. And we either look on a table or we use that table to calculate a delta H naught. And what we get is delta H naught is 6.037 kilojoules per mole at 0.0 degrees Celsius. I have a delta H and I have a T. So what can I do? I can calculate a delta S. Now, delta S for this process, right, is unknown, but we can calculate it using this formula. And in fact, because we're using an H naught here, this would be delta S naught. Well, we get to assume this chapter, well, we get to assume this year until we get to physical chemistry your junior year, if you're a chemistry major, is we get to assume that these guys are temperature independent, which means that they don't change as the temperature changes, all right? Delta S naught and delta H naught, right? Which isn't actually true, but it's an assumption that we make this semester. So delta S naught, oh, I actually kind of know what it is already. Right? All I need is delta H naught and RT, right? The T that we're doing this measurement at. So for this example, we're gonna write it as 6.037 kilojoules per mole over T. Now guess what we're gonna have to do with T? Our T's are always going to be in Kelvin, right? So at 0 degrees Celsius, that's 273.15 Kelvin, right? We do the math here, and you can check my work, please. And what we get for delta S naught for this process is we get delta S naught is 22.11355 joules per mole Kelvin, okay? Now what I did is I took joules and kilojoules and I made it joules because that's how you'll see delta S's and also S of formations. That's how you'll see them reported, joules per mole Kelvin. Do the units make sense? If I go up here and look at my units, this is kilojoules or joules per mole. There's a per Kelvin here, a per temperature here. The units make sense. Does the sign of delta S make sense? All right. We get a positive value for delta S. Come back up here and look. What reaction are we analyzing? It's actually not a chemical reaction, it's a physical process, but it's written like a reaction, and we have one solid thing going to one liquid thing. We increase the motion. We increase the disorder. So I come down here, my delta S is positive. That answer makes sense. Okay? So this is how we can get delta S's. We often get them from delta H information. So if this is how we can get delta S's, I'll show you two different ways already. We can get it from this equation, or we can get it from that table. All right? And we can do that little step that I said you had to review about delta H, and we could do it with S, right, from tabulated values. We can get delta S for the system numerically this way, okay? So if we can figure out a way to get delta S for the surroundings, okay, then we'll be able to get delta S of the universe. So remember, delta S of the universe, we need both those parts, delta S for the system and delta S for the surroundings. Well, delta S for the surroundings, all right, has a similar equation. Delta S for the surroundings means we need to figure out the heat that goes into the surroundings, and we need to know the T of the surroundings. So really it's the same equation from before, except we're not focusing on the system anymore, we're focusing in on the surroundings, okay? But the heat that goes into the surroundings is opposite the heat of your system. If you think about the way we have things defined, okay? Where does that heat from the system go? It goes into the surroundings, right? You remember doing problems last semester where Q equals minus Q was a starting point because heat flows from one object to the next, right? That heat is equal in magnitude but opposite in sign. So if I can figure out heat of the system, the opposite of that is what went into the surroundings, right? If the energy is released by the system, it's gained by the surroundings. If the energy is gained by the system, right, the surroundings released that energy into the system. They're equal but opposite in sign. So then that brings us to, all right, oh, well, that heat is often isobaric. Oh, that looks like minus delta H for my system divided by T for the surroundings. So it looks like you have a lot of the information now you need about the system that can be taken and inferred as information to the surroundings. If I figure out my enthalpy change for a process, the opposite of that is my heat of the system or surroundings, all right? My system gives me information that I can take the negative of to get information about the surroundings. T of the surroundings, right, is set. It's something that's usually given in problems. It's also something you can substitute in there, okay? So this is another equation that we need to be aware of and be able to use. Once I get both delta S for the system and delta S for the surroundings, I have enough to get delta S for the universe. So to drive this home, let's do one last example this video, okay? And let's talk about H2O solid to H2O liquid again. But let's do this at a couple different temperatures and let's make sense of the results, right? Let's start off at 0 degrees Celsius. Let's say we run this open to the atmosphere and we're at 0.0 degrees Celsius. That's our starting point for this first part of this example. Okay, and what we want to know is we want to know what delta S of the universe is equal to. Well, delta S of the universe means I need delta S for my system, and then I also need delta S for my surroundings. If I add those together, I'll get delta S of the universe, and then that will tell me if the reaction or the process happens or not, okay? So then imagine, this is piggybacking off the last example we did where we knew delta H, all right? So delta S naught, we already know. We already know that delta S naught is 22.11355 joules per mole Kelvin. We have that from our last example. We could calculate that with table information because it is standard, but we have it from the last example. How are we going to get delta S for the surroundings? Well, delta S for the surroundings is minus, and this is under standard conditions, minus delta H naught over T of the surroundings. That's the starting point we just talked about. All right. Well, T of the surroundings, that's the same as the temperature of the system. It's still 0 degrees Celsius. So this looks like, minus 6.037, right, times 10 to the third joules per mole. It's kilojoules per mole, but I did the 10 to the third right there, just automatically. Divided by 273.15 Kelvin. Okay, so now I see how this works. I just take the delta H, I change its sign. The delta H we were given in the previous example was this. I take the negative of it. I divide by the surrounding temperatures. It says we're at 0 degrees Celsius. Okay. So, wait a second. I get delta S for the surroundings to be the exact same number that we got before, but opposite in sign. So at 0 degrees Celsius, right, at 0 degrees Celsius, delta S for the system and delta S for the surrounding, they're equal but opposite for this process. And all I was given was a temperature and a delta H. And so what I get for delta SU is 0. Now, why is this important? Whenever you get a delta SU, that's 0, what that means is your system is at equilibrium. That means there's no net motion in one way or another way. Okay? You are at equilibrium. Okay? That makes perfect sense. What's special about 0 degrees Celsius for water It's the melting point. It's the freezing point. It's where solid and liquid coexist in equilibrium. Using our definition from earlier in the semester, whenever you get a delta SU that's 0, you are at equilibrium. And that was actually an expected result here. Okay? So there's no net motion. We really can't talk about any changes in, as it's written, the change in disorder is still positive. Because if there would be solid going to liquid, it still would be increasing disorder. But delta SU tells us about whether the process occurs or not. And this is saying, well, it happens, but it's in an equilibrium way. There's just as much this as there is that. So let's change this up and let's see what happens if we make slight modifications, right? Let's run this at 10 degrees Celsius instead. Delta SU is still going to be delta S for my system plus, I keep grabbing this marker, it doesn't really work, sorry. Delta SU is going to be delta S for my system plus delta S for my surroundings. This is done under standard conditions, so we can put little knots here. We could even put a little knot above delta SU if we wanted to. Okay, we're running these at standard conditions. We'll do some work under non-standard conditions in the next section. Okay, delta S naught though, it doesn't change. Remember what I said we get to say here? Once you know delta S naught, you're set. You know it no matter the temperature. This semester, we get to pretend that it doesn't change. So if I know delta S naught, right, here it is, all right, it's still this number. Delta S naught for the surroundings, though, does change, right? Minus delta H naught, okay, that doesn't change, but what matters here, the big difference between these last two examples is that T surroundings has changed now. So you go to set up all your same math. You're using the equations that we used, the H over T, right? H over T doesn't change for the system, but H over T does change for the surroundings. I remember my negative sign, but now down here, this is 283.15 Kelvin, right? I do that math now, and I don't get a number that's equal and opposite the system number. When I do delta S naught for the surroundings now, okay, what I get is a situation, right, where the number is 21 with a negative sign out in front, 0.3209 joules per mole Kelvin. Oh, okay. So I come back up here now. I have a number I can put in for delta S naught. That number goes there. I have a number I can put in for delta S for the surroundings under standard conditions. That number goes there. I do this math now for this example, and what we get is a delta SU that is equal to 0. All my markers are dying. We get a delta SU that's equal to 0.7. All right. That's the rounded value. Let me get the unrounded value. 0.79269 joules per mole Kelvin. Delta SU now, right, is positive. How do we interpret delta SU being positive? This is the important delta S. This is the important delta S because it tells me whether something happens or not. Delta SU is positive, linking that to the second law. When delta SU is positive, the process occurs. The process occurs spontaneously. So at 10 degrees Celsius, we had the same delta S naught, but delta S naught for the surroundings changed, and so delta SU changed. We get a positive value that makes sense because at 10 degrees Celsius, will ice melt? Yeah, you're above the melting point. So at 10 degrees Celsius, what's telling me thermodynamically that ice melts is delta SU is positive. Okay? Incredibly powerful, incredibly important example. I'm going to just give you the values. I want you to kind of do this yourself. Do this exact same analysis, and I'll kind of walk you through it a bit right now. But I want you to fill in the gaps mathematically. It's good practice. Do this exact same analysis at minus 10 degrees Celsius. Right. Ask yourself, does delta S not change? Nope. Once I know this for the system, we pretend it doesn't change. But what does change is delta S not for the surroundings. So think about how you're going to account for that change. What you get for delta S not for the surroundings in this case. Right? And like I said, check my number as always. Okay? What you get out is a different value. Actually, what I'll give you is delta SU. All right. You're actually going to get a number that's going to be bigger than 22.11. Right? It's going to be some number that's bigger than this. Okay, so delta, let me write it mathematically correct. Sorry about that. Delta S for the surroundings is going to be bigger than 22.11355 joules per mole Kelvin. And that should kind of be an expected result. Delta SU, then, when I add these two numbers together, right, is going to give me a negative result. And what I get when I do this math is I get negative 0.8277 joules per mole Kelvin. Delta SU in this case is negative. So at negative 10 degrees Celsius, what I get is a negative delta SU. How do I interpret that result? Well, for all spontaneous results, delta SU must be positive. So at negative 10 degrees Celsius, will solid turn into liquid? Well, no. At negative 10 degrees Celsius, we're below the melting point. What do we actually expect to happen below the melting point, right? Below the melting point / freezing point, liquid should become solid. So whenever we get a negative delta SU, what that's telling us is that the reverse reaction happens. The reverse reaction happens. The reverse reaction is spontaneous. And that's why I've been careful to write this like an equilibrium. Right? So one quick little summary, because we went over a lot of important things. And this is everything that you need to be able to sort of digest, all right, about this video and everything we've talked about with entropy so far. All right. All right, summary. Delta SU predicts spontaneity. It tells us whether something happens or not. When delta SU is equal to 0, you're at equilibrium. When delta SU is positive, then that means it happens as written. It's spontaneous. It will occur. When delta SU is negative, it won't occur as written. And in fact, all right, the reverse is spontaneous. It's almost like delta SU tells us like Q versus K, which is a connection that we'll make eventually here, right? It tells us whether at equilibrium, whether it's written and is going to happen left to right, or whether as it's written is going to happen right to left, okay? The way you get delta SU is from delta S, right? Delta S for your system measures disorder. It doesn't measure spontaneity. It measures disorder, and that's it, right? Delta S for your system, right? When it's positive, right, disorder has gone up, right? Delta S for your system, when it's negative, disorder has gone down. The system becomes more ordered when it's negative. The system becomes more disordered when it's positive, okay? We can calculate delta S. We often do it under standard conditions by knowing delta H over T, okay? delta S also exists for the surroundings. And we usually don't talk about this in terms of a positive or a negative and what it means to the surroundings, because the surroundings are just so large. But do know that it does measure disorder. And what you need to know about delta S of the surroundings is you can calculate it from system information. You find the delta H for the system and you take the opposite sign, right? This is often done under standard conditions, so I'll just put the knots there, right? It doesn't have to be, but it often is. The big difference here is that you always divide by T of the surroundings. So where delta S naught is set, no matter what temperature you're at, delta S for the surroundings will change based off of this temperature. It'll always change based off of that temperature. So delta S for the universe is delta S for your system plus delta S for your surroundings. And that's how you can decide whether something's going to happen to the left to right, right to left, or whether it's at equilibrium. Okay. As always, send me your questions. We go on to talk about a different thermodynamic property next that actually relates to spontaneity as well. This is kind of annoying to do, actually calculating these separately. So what we do is we kind of think about a way to get at delta S universe in a much more efficient way. And that'll be the discussion that we have next time.